My name's David Upton. I'm grandly described as the exhibitions manager for the Computer Art Society, which means I'm the man with the blue tack. But I'd like to ask Professor James Davenport to give us a sort of introduction to the whole question of quantum art. James.
Thanks, David. Thanks very much for inviting me. So I'm James Davenport from the University of Bath. I've just ceased being a trustee and a council member of the BCS. Literally last week, but I've been involved in BCS for some number of years. This is a very interesting joint meeting. I come to this largely from the quantum specialist group where I'm the treasurer. So I hope we get a sort of twin flavour of the event. So BCS itself was established in 1957, which is a long way back in the history of computing, if you think about it that way. Lengthy royal charter, because all royal charters are lengthy, but we've summarised it in a very simple phrase: making IT good for society. It's very broad remit, as indeed this meeting exemplifies by being half quantum, half computer arts. And there's also, for example, a digital device specialist group and many, many others. And you can find their list on the website and so on. Quantum technology is a fast-moving area, growth area in all sorts of ways, notably in quantum sensing, actually. It's worth mentioning that, which is a very much growth area. And in UKRI's United Kingdom Research and Innovation has greater than £1 billion over the next 4 years in quantum research. That's great news. The bad news is that quantum computing does not get all of it, or even most, or even much of it. Despite the hype, quantum computing is not, frankly, let's be honest here, the flagship of quantum technology. Quantum sensing is. Quantum computing is good and important, but you know, it is not the only quantum subject anyway. It is advancing in at least two very different directions. And when I lecture quantum, I sometimes say it's a bit like the difference between analog and digital computing. And both compute things in very different ways. One way is adiabatic and quantum computing and quantum annealing, which is basically an optimization technique. D-Wave is a big American computing company. Oxford Quantum also produces computers in this area. And customers, as well as research labs and so on, well, they would do, wouldn't they? Include, for example, Delta Airlines. So we have a real business putting real money where it is. The other direction is so-called gate-based, which is where you've probably heard about it. It's quantum bits, qubits, and how qubits evolve and interact and act in superposition and entanglements and all those magic words. Potentially, it offers very dramatic speed up on specialist tasks. In some sense, the more specialist the task, the greater the speed up, which is perhaps slightly unfortunate. For example, it could break all current public key cryptography if it was big enough and effective enough. But it's very error prone, much more error prone than the adiabatic one, which is why the adiabatic one is having more success in the commercial market. And it will need a factor of 10 to the 12 improvement in error correction before it's actually capable of doing what I've said on the slide. Well, in perspective, there's a factor of 10 to the 9 between the Wright brothers' Kitty Hawk flight and the round the world flight, which happened the first time a few years ago. So that took sort of 115 years to get a factor of 10 to the 9. So I look at 10 to the 12 and say, possibly. But nevertheless, it's very exciting. Potential impact, optimization. It's in use already, as I said, particularly in an area that we don't do very well classically, which is so-called mixed integer linear programming, where you've got both real-world variables like the amount of fuel an airplane uses, and integer variables like which kind of airplane will use and how many crew it needs, and so on. You can't, if a plane's half full, you can't fly with half a pilot, and that sort of thing. And those are problems that classical computing does not do very well at. Which is probably why Delta's bought it, and I didn't use airlines by accident, as it were. Simulation. Especially simulating materials, simulating proteins, and so on. And here people tend to build specialist hardware where essentially you always have quantum simulating quantum, which is, of course, very effective. But again, potentially very powerful. Cryptography. Again, it's not clear here because of the error correction problem. But undoubtedly, we must allow for it hence the whole field of post-quantum cryptography, which is what should I do if I'm worried that you might have a quantum computer? And so on. That's a very important field, and a lot of research and development and deployment is going on here. And there are standards saying you must transition to it by 2030 and so on. Machine learning. There's a great deal of hype in this area, frankly. The problem is that most machine learning is data heavy and comparatively compute light. Yes, I know people say they buy these thousands of NVIDIA GPUs and so on, but per data item is actually still pretty compute light. Whereas quantum computing is very much data light and compute heavy. So there's a pretty fundamental mismatch here as far as I'm concerned. I personally, this is personal opinion, do not see quantum machine learning as the replacement for the existing technologies just because of its mismatch. Doesn't mean it's useless. After all, in some sense, machine learning is a matter of optimization. I'd just say it's very useful for optimization. So if you get a particular optimization problem within that, which is more data light and compute heavy, great. I was trying to look that up just recently while preparing this talk. I came across a really quite good picture which has classical data, classical algorithms, quantum data, and so on from a, no, I meant to have the reference here. I haven't got the reference here, sorry. But yeah, so quantum machine learning could mean a lot of things. Throw together two buzz phrases and you get a mess, as always. But I don't see it as being the answer to the world's problems for the reason I've mentioned. So what's BCS doing about quantum? Well, last year we established a quantum specialist group. We had our initial quantum event only event where we're scheduled for next week. There's the Eventbrite link there. You can search Eventbrite and so on. And it's probably not escaped your notice. There's also a tube strike next week. However, it's a hybrid event anyway. So we're almost certainly, unless BCS headquarters say it won't work, we're almost certainly going ahead with it. And I'm pretty sure we'll go ahead with the hybrid side at least. It's a hybrid computing current state overview. What is computing? Why do we need it? And it's going to be a bit like my talk, but much better sourced by real experts and so on. So BCS is moving ahead very much on quantum these days, but quantum is hard to explain and understand. I say this with feeling as someone who has to lecture it. And so all sorts of analogies, images, and so on are useful. So as was said, the trains are not behaving, so I haven't had a chance to look at the exhibits yet, but I'm hoping to be much enlightened by what they'll tell us about it. The tube strike, so the current plan is maintained as hybrid. That's it, yeah. Okay, thank you.
Thank you very much. I'm glad you said quantum is difficult to understand. Makes me feel a lot better. I'm just an ordinary artist. I don't know anything about, I got an arts degree and all that sort of thing. I'm not a technical person, but I'm looking at the whole question of quantum arts and what does it mean, and trying to put together something which would help working artists to take decisions about whether they ought to be involved in quantum arts or whatever. And so I hope this meeting will enable you to take away some ideas and new inspirations. What does quantum mean? Well, the official definition is it's the smallest amount or unit of something, especially energy, in physics. It's started being used in that sense by Einstein in 1905 and Planck in 1906, so it's not that new. Originally, we thought since Democritus in 400 BC, the world was made up of atoms, and atoms were things you couldn't cut anymore. An atom was the smallest unit of whatever. But rather than split the atom in 1932, we now have subatomic particles with sillier and sillier names. Some are actually being seen and some are just expected. But the problem is, as you get below a certain size, these things all start to behave differently. The rules don't apply. Rules of classical physics, for instance, most typically, sometimes they act like waves and sometimes they act like matter. And according to classical physics, you can't be both. And the second problem, I think, which intrigues me, is that we all accept that chips are becoming smaller and smaller, And these strange effects are, of course, starting to appear as the chips become smaller and smaller. The effects are starting to happen. Things are going places they shouldn't go, so on and so forth. So what we wanted to do was to help artists to make sense of this difficult area, because it is an interesting one with all sorts of fascinating areas for art. The first problem, as James hinted at, is the different language. You know, is it quantum computing? Is it quantum physics? Is it quantum mechanics? What is it quantum art? What are we talking about? We chickened out of that. We just called this talk the Q word. So sorry about that. It seems to depend really who you're talking to and when you said it. We've tried to put a certain amount in about theory, but I won't bore you with that tonight. We've produced a book here. You see there are little stickers up all over saying how you can order the book from Amazon with a QR code.
Can you just show that book again? Let's get a little clip of. We've Astrid who ordered it.
Yes.
Absolutely no interest in Q probably anything.
Well,
but then I wanted to come here to learn something.
Yeah. Well, you know, it's a strange situation. We are. It's almost deja vu for the Computer Art Society. We were founded in 1970 after an exhibition called Cybernetic Serendipity at the Institute of Contemporary Art, which was a lot of people saying, what could they do with a computer in the art room? You know, all sorts of silly things. Some of them really quite groundbreaking, even now, and some of them rather obvious, but they weren't obvious then. What happened after this exhibition? Everybody was very inspired. Lots of people wanted to take the conversation further. The Computer Art Society was really a group of people who were prepared to talk to each other about computer art, whatever that was. Also, very practical point, one or two of them actually had computers, you know, good old-fashioned ones, which they would let people play with. And we see ourselves almost the same way. You know, if you're an artist nowadays, trying to come to terms with quantum computing, what is it? What's it mean? It's very easy to feel a total fool when this happens. So we've tried to put together something which will just guide people through this. We've got three really good speakers. First of all, Astrid is going to offer some practical quantum tool, which you can actually download. We've got the instructions for that here, and you can use in your own practice as a quantum art tool. Sarah Selby is going to set it in context, talk about the sometimes Faustian pact between artists and big tech. And Ola Bamboy is going to look at a practical new going to look at a practical new paradigm for classifying, conserving and experiencing art that crosses over historical and colonial boundaries. We've also got some exhibits to come up on the walls in the corridor there behind you and in the room next door. We've got practical examples of works by Ernest Evans, Jonathan Knobloch, Whitcomb Hazine, Astrid Park, Ola, even by me, to show different artistic approaches. And in particular, we'd like you to experience Ola's and Astrid's work for yourselves later when we leave the lecture room and go to meet the artists, see their works over a glass of wine, see two working installations. As it happens, 2025 was the year of the quantum. We're only a year late. I think that's not bad, really. But there's fascinating misuse of the word. There's a picture in the book of a thing called the quantum dishwasher tablet, which presumably means that that dishwasher only improves the cleanliness of your dishes by the smallest possible perceivable step.
Sounds fantastic.
But the question is now the right time? And well, James has answered that question, I think. The Economist agrees. The Economist thinks that some even wonder whether quantum could be bigger than artificial intelligence, whatever that means. Okay. How do you measure success? I mean, can you get your hands on a quantum computer? No, you can't unless you've got a lot of money, but you can get your hands on a simulator. Personally, I feel, you know, it's all very well saying it's a simulator, but this is an accurate simulator. I don't know whether we actually know that. It seems to generate largely on how many data units you can actually handle, but we're not really interested in getting too technical at this stage. But it's interesting that Google, only last October, announced the first demonstration of verifiable quantum advantage. In other words, the first time a real quantum computer has been faster than a simulation running on a very powerful classical computer. And we're into acronym land again. currently were NISQ, noisy intermediate scale quantum machines, NISQ. Noisy means they're not very good simulators. They invent things that shouldn't be there, or they miss things that should be there or something. But the next stage has its acronym, but I don't think it's got any machines yet. That's called FTQC, or fault tolerant quantum computing. Once running, then they'll come into their own. And I think James mentioned the breaking the RSA encryption algorithm. And it may well be, given the secrecy that surrounds these things, the first inclination we'll get of a real quantum breakthrough will be Mercedes-Benz and Rolls-Royce sales to medium-level civil servants in Cheltenham. Anyway, the only other question I wanted to raise, and we've referred to it in the book, how do you know whether you're actually doing quantum art or whether you're just using the buzzword? There's a very good academic paper which we summarised, which looks at not quantum art but quantum games, and comes up with 3 criteria. One is it about quantum concepts such as entanglement? 2, does it run on quantum hardware or software? And 3, if not, does it still have a solid connection to quantum physics, e.g. by simulating a process? So if you meet those tests, we reckon you can call yourself quantum art. Talking about quantum art leads me on to a company called Moth Quantum, which has been set up in London as a startup, primarily to introduce quantum to the arts, in the broader sense of the word. And our first speaker is Astrid, who's going to talk to us now about, well, I'll hand over to Astrid.
Hello, everyone. Pleasure to meet you and welcome to the QWord exhibition. I can see my colleagues, my friends, everyone here. So yeah, again, thank you for coming. So I'm Astrid, and I'm working in the quantum computing startup called Moth Quantum, which is based in London. Actually, the building called Somerset House, right next to Liberton, so it's such a beautiful place to work with the quantum simulation and quantum hardwares. But anyway, we are mostly focusing on how we could introduce quantum computing to artists and creative technologists so that they could actually download or get some hands-on experience with quantum hardwares, with the software or any other experiences that we build. So I'm the quantum application engineer, so I'm mostly doing that. And Harry, my colleague over there, he's the mastermind, the quantum software also. So we are working together and bring this dream all together. So today my talk is about how I used and how Moth used quantum technology in the artist creative making. So we are mainly focusing on the deployable applications, which AKA it means that it's for artists, it's for users, user-centralized applications, rather than just summarized PDFs or something like that, or some very, 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 very complex, some equations. I think you might have seen something on the corridor, which it's the mixed combination of Greek alphabet, but no, there won't be Greek alphabets in this slide, so stay tuned and stay relaxed. So I briefly introduced myself. That's me having fun in Berlin Science Week last year, where I introduced quantum brush. But anyway, so I studied MSc Creative Computing in University of the Arts London, which is based in multiple locations in London, but mainly in Camberwell or CCI and High Holborn. And yeah, creative computing is my life passion. And for me, like providing some experiences using creative computing, but especially using quantum computing backend is always my life passion. And luckily I really enjoyed my studies in UAL CCI, and now I'm here working in Moth Quantum. So my goal is bringing inspiration for creative technologies and artists and making tools that people can actually use. So let's move on. So I think the biggest question for myself also, and what I always ask is how quantum computing become a creative tool for supporting artists and creative technologists. So during my MSc years, I actively researched through how quantum computing and artistic practice can be connected. And I used some research methods called ethnographic drawings and analyzing the impact of built environment in the post-human making, for example. So I just wrote some kind of essay called suggesting the keyword called agential design, which is the post-human approach for computational design protocol. In the easy words, I kind of researched how can I use quantum computing, quantum simulation to make urban design practical and useful for the actual users, especially focusing on demystifying universal design. And I personally believe that was a really good start because I gained some courages while doing my research. And yes, and I made the tool for the early start. So I mean the URL is on top of there. Sorry, I didn't put up the QR code, but it's the very simple, no login required, no credential required quantum computing library called Moth. It's continuing the legacy of MicroQISC, which is developed by IBM long time ago. Before they officially launched QISC version 1, they supported the very simple version of quantum simulation for classical hardwares through the library called MicroQISC, and now it's deprecated. But to continue introducing quantum computing for creatives, me and my other colleagues connected those legacy in the name called Moth, because Moth is our company name. And that exhibition that I've done back in 2024 December, I think, and it actually used those quantum computing library with the physical computing practice. So if anyone in this room have any interest in using Arduino or anything, I made Moth for Arduino, which is the world's first quantum computing library for ADR chip microcontrollers. So anyone can download it and bring their own creative practices for physical computing. So here,
where do we download it from?
GitHub. So there's I mean, there's the thing called GitHub, and it's kind of a what is it? A vault for codes. So it's open source. The good thing is it's open source. Anyone can download it. Anyone can contribute it. Anyone can use it. So if anyone have any interest in physical computing, highly recommend this one and just start out building some things. And for my MSc thesis, I just made this kind of moving kinetic sculpture over there, which is based on the interaction between that imaginary creature furball over there. And based on the interaction, it will build quantum circuit based on your interaction between the surrounding environment. And it will calculate the results. And it will generate music using wind chimes up there. And actually, if you search Google about quantum computers, then quantum computers actually look like some discs on the ceiling with some very weird wires and very weird pipes, something like that. So the motivation is all based on quantum. So now, after this MSc years, I'm now working in the industry. Of course, continuing the personal research is extremely difficult. For me, it was very difficult. But another thing that I really enjoy now is, as I've said, making tangible use cases of quantum computing for creative industries. And that's what Moth is focusing on right now. So I'm keep going now. So what have I done while I'm keep going? So again, Moth, I introduced this already, but I recommend while you're using these tools, you can ask these 3 questions. The first one is what is the quantum circuit? Like, quantum circuit is basically the series of operations on qubits, but how it will bring changes and how is it written? And you can kind of easily explore through it using Moth because it's all the codes are open source, so anyone can view it. So let's move on to the next one. And the next one is literally on the next room. And the piece is called Reality is Not What It Seems. Why? Because it uses algorithm to detect faces. And after it detects faces, it will encode your faces. It's not doing anything serious, not like doing something weird with machine learning. No worries. It's just it's detecting faces through OpenCV Python, and it will encode facial data onto the quantum circuit, and it will decode it and put it onto the live stream. And the algorithm is called QPixel. It's on the Nature paper. You can actually search through the GitHub repository, also search on Google. Then what is this? I wanted to talk about that we are looking through this world through our eyes, but how about imagine like how those tiny quantum level interactions are happening in even right now, or even in the quantum hardwares. And that's the thing that I wanted to imagine. And it's actually using deployable quantum computing algorithm. So, and it was really good piece. And now it's after London Tech Week and Science Gallery London exhibition, and now it's here. So feel free to go to the next room after the talk and yeah, actually have a look. And the next one is Quantum Brush, which is me and my colleagues and collaboration between Moth and DESI institution made. And obviously it's also an open source tool, and you can download it on our GitHub. You can search on Google, and if someone is really want to deep dive into those Greek alphabet things, you can read the paper also. And what this is about, so this one, we actually connected those algorithms to IQM, which is another quantum computing startup, IQM's Sirius QPU, and we executed those quantum algorithms to actually make the visual effects from the user interaction. So imagine it's literally a brush, and imagine you are drawing something, a brush stroke on the canvas, on the image, and it will introduce new effects based on the quantum algorithm that me and my colleagues developed. And that's what Quantum Brush does. So it's actually showing the noise, the NISQ device that David briefly mentioned. It's kind of actually useful in the creative industries because those noises can also introduce some weird effects that we didn't imagine before. So that's what Quantum Brush is, and it's obviously because it's an open source tool, it's also used in various hackathons like military design and platform quantum hackathon last year, and it's introduced in Berlin Science Week. So I really do hope that this one can actually show what quantum visual algorithm can do onto the visual effects, and have a look at the algorithms, also have a look at the code and see how it goes, because everything is there, and you can also make your own brush following the manual. So yeah, have a look at this also. Another thing that I'm working on and my colleague worked on is called quantum awesomeness. It's based on the quantum hardware benchmarking, but it's bringing those benchmarking processes onto the format of puzzle game. So why benchmarking is important? It's because, like David said, now the quantum devices are heavily kind of affected by the noise from itself and the nature, the surroundings from those QPUs. And that's why error mitigation is really important. And that's why benchmarking is also introduced, because obviously we like benchmarking for our iPhones, laptops, and anything else. We want to contribute. We want to think about how these QPUs or CPUs or whatever, even graphics cards, are different from each other. Which one is powerful, which one is faster, etc., etc. And for quantum device benchmarking, obviously we need to measure how the noise is managed and how this noise are controlled. Is it decreasing? Is it doing well? Its calculation is trustworthy or not? And that's why it's useful. But obviously it's four of those equations. And that's why my colleague James Upton, he made quantum awesomeness algorithm, and now this quantum game is showcased on last year's Gamescom. And now I'm also working something behind the scene, bringing another format of benchmarking with my colleagues. So I think this is also a good example of how QPU can also be used to make some fun use cases, not only about all of those mathematical tables and all of those test data. And the next one is also on the next room. It's called Quantum Photo Booth. It was happily it was a mega hit on last year's Science Gallery London. So there was we contributed something called Quantum Untangled. I think the exhibition is still going on, but there was an event called Quantum After Dark, and that's what Moth Quantum actively contributed. And Quantum Photo Booth is using the algorithm called Quantum Blur, which is actually introducing the blur effect, but it's not just the Gaussian blur or something like that. It's actually bringing those pixel data onto quantum circuit, and it will apply some kind of blur effect using the gate-based quantum algorithms.
Can the blur effect make us look younger?
Sadly not younger, but you will be pixelized.
Yes. Airbrushed.
So yeah, so the examples are actually there, and you can also have fun. You can bring your picture back home. Anyway, so it's also kind of a very, very fun example of actually doing something with quantum algorithm. So it's kind of demystifying all of the examples here. It's actually demystifying the quantum. It's not only the ones that you need to sign up somewhere, for example, IBM Quantum Platform. You need to download the token, you need to set up the token, you need to send the job, you need to wait. Everything's not there, but actually you can actually have fun. You can draw, you can take a picture of it, you can see your face encoded and decoded on quantum circuit. You can download Micromoth, use for your own robotics or physical computing applications, I don't know, but you can do a lot of different things using our open source tools. And these are confidential projects, but I will briefly pass through, but one of the examples that if anyone works in audio visual programming or something like that, DJ set, Rave, no, okay. So there's the tool called Touch Designer, which used so many artists and creative technologies in all of those venues and live visual interaction, audio interaction. And I'm using quantum computing, the real actual communication between quantum lab and my software on Touch Designer. And I'm working on that one, but sadly cannot talk about it more, but just think about it. Just using visual programming tool with quantum computing, and it's inviting people to use it when it's installed in somewhere. Hopefully you will be there also. And so what I'm doing now, so I'm doing practice-based research for using a lot of research methodology. And I'm actively bringing industry experience for long life cycle of my research output, because I really want people, like 4 people, to actually use my tools or have fun with my research output, not just looking at the people like, oh my God, this equation is cool, and move along. And that's my kind of philosophy of why I'm doing this and how I'm doing this. So hopefully my talk will give a little bit of inspiration or some kind of a courage for your artistic practice. I really hope so. Yeah, so these are the sources. Yeah. And I'm on Instagram and LinkedIn or wherever, so keep in touch, and thank you for listening.
Anybody who wants to know more about the quantum brush, we've got a sheet here which tells you how to download it and how to use it. There's sort of on the front desk. Thank you. Moving on slightly with a different approach, I'd like to ask Sarah Selby to come and talk to us about put it all in context. You know, where do quantum arts fit in with the rest of the world, so to speak?
Sort of. I went there, yeah. I mean, I chose one part. Hi, my name's Sarah Selby. I'm an artist and also a researcher. I'm based at the University of London's Creative Computing Institute, which is also where Astrid graduated from. So we actually meet quite a lot in passing and know of each other's work very well. We also met at this residency called Studio Quantum. So this is where I sort of began my journey exploring quantum computing as an artistic medium with Kerry as well over here. So Studio Quantum is a residency organised by the Goethe Institute. They've been doing it every year. I think it's on its like 4th cycle, maybe. I'm not sure if they're running one this year. Would recommend looking into it if you're an artist and you're interested in exploring quantum within your practice. But the way that it works is it takes artists and it pairs you up with cultural institutions as well as research institutions. So you sort of work between a university and a cultural institution to explore quantum and its potential. So I was based in ZKM in Karlsruhe for 2 months, working with actually researchers from Karlsruhe Institute of Technologies, the political science group. So it was much more about the kind of political science and thinking about what quantum and quantum computing means for society more than so much of the literal application of quantum within that. So during my time there, I spent a lot of time kind of thinking about learning about the geopolitical tensions of quantum computing, as well as the sort of policies that are being developed around it. So whilst I was there, I was really sort of struck by, as David said, the parallels between quantum art and the early computer art, and what we can kind of gain from early computer art as a kind of medium to apply to this kind of new quantum art scene. So quantum is often used to help, quantum art is often used to help explain quantum science to the public, but it actually does a lot more than that. It shapes how we understand the technology culturally. So it shows that quantum tech is not just scientific, but it's also a social and a political technology. So artists are working at the moment to explore some key quantum ideas through their work. There's some terms that you'll hear quite often through quantum art. One of them is superposition, which is the idea that a quantum particle can be in multiple states at once, which I'll talk about a little more later. There's wave function collapse, which is when lots of possibilities become one outcome. And then there's also something called amplitude amplification, which you don't hear about so much, but it's basically about increasing the likelihood that when a system is measured, a certain outcome will appear. So the concepts aren't really just explained, but they're also expressed through artistic practice. So yeah, my book chapter talks basically about the parallels of quantum art with earlier computer art and the role of the artist and the audience imagination in shaping technological futures, as well as art as a tool for either what we call constructive or destructive interference, which again comes back to amplitude amplification, which I'll talk more about at the end. So these are just some images of one of the earliest commercial computers that was used. This was a computer called the IBM 7090. This image is actually from AMAS, one of the NASA research institutions, but it's a computer that was also at Bell Labs, which was one of the main areas where artists could access computers through collaborations with researchers and scientists. So quantum computing at the moment is at a very similar stage, again, as David said, to computers when early computer art emerged. Quantum computers at the moment are very, very large, expensive devices. You can see an example of a quantum computer on the right there. As Astrid said, they look like these sort of huge chandeliers, most of which is actually the refrigeration, because quantum computers need extreme cooling in order to maintain superposition. So artists in the early days of computer art often worked alongside scientists who were working on projects for military, including things like missile systems, submarine sensors, and also enciphering machines. And very similarly, much of the quantum infrastructure is heavily funded by the defense sector as well. So artists working with quantum and negotiating these same kind of tensions and contradictions when they're working with quantum computers. One of the differences, I think, is that quantum computers are now accessible via the cloud. So you don't need physical accessibility to a computer like the early computer artists did. But not all of the early computer artists actually needed physical access to the computers in order to make work about computers and what computers meant for society. So on the screen at the moment is Vera Molnar's Machine Imaginaire. And she created rule-based algorithmic systems for making art, and she called this the Machine Imaginaire, or the imaginary machine, where she followed rules manually and she used her own body as the computer to kind of execute these artworks. And she showed that kind of computational art can exist as a concept and not just the technology. So even though she did move on to using pen plotters to execute her self-designed algorithms, she was experimenting with the concepts and the ideas behind computation in terms of algorithmic art and like generative systems much before she physically had access to systems. So I think that we could reflect on how we might begin to start exploring these quantum ideas even if we don't have direct access to quantum. Mona's work is often also talked about one of the main things about it is the kind of human aspect that she brings to these computational processes. And much like other artists, some of her work questioned about whether complex human experience can be reduced to a binary logic. Artists were very interested in systems thinking and this idea of systems design in the early computer days. So it becomes this idea of kind of introducing disorder is common for our early computer art and becomes especially visible in later conceptual media art. Another one is Frida Nake. So Frida Nake, actually, he wrote this piece on the right here, which was called There Should Be No Computer Art in 1971. So although he worked directly with computers in his practice, he argued that computer art risked reinforcing dominant power structures. And he argued that aesthetic experimentation alone isn't enough, and artists must confront the politics that are embedded in computation. He pointed out that computers are not neutral tools. At this time, computing was being used like much more heavily in military. It was around the same time as the Vietnam War, which caused an outcry. And these computers were coming from military and capitalist systems, and that computer art risks reproducing those systems, and art should critique and not just use the technology. Sorry. So along those same veins, there are many artists that are working with quantum computers that are also kind of interrogating the ethics and the implications of quantum computers. So I wanted to think about some of the fundamental differences between a quantum computer and a classical computer and what that might mean for quantum as a medium versus classical computing. So one of the ways that artists explore this is the idea of state representation. Much like early computer artists were looking at the idea of algorithmic generative systems in this binary state of 0 and 1. Quantum uses qubits, which can be in superpositions of 0 and 1. Another difference is computation. So with classical computers, we use deterministic or probabilistic sequential operations. In quantum, we use something called unitary operations, which manipulate probability amplitude. So rather than actually designing or engineering the specific outcome, we're engineering the probability that this outcome will emerge. So we're actually focusing much more on the landscape around the outcome and trying to make that outcome emerge. The outcome is, in computing, a single deterministic value after computation, whereas for quantum, the outcome is a measured result, which is one possibility sampled from a probability distribution, which is engineered in the previous step. And the result is not generated until observed, which is one of the hardest concepts to get your head around with quantum computing when you start working with it as an artist. So this is the famous Schrodinger's cat, and I didn't want to include Schrodinger's cat because Schrodinger's cat appears in absolutely every single quantum talk that we see, but it is a helpful way to kind of visualize the idea of superposition. So Schrodinger's cat, it's a thought experiment by Erwin Schrödinger to explain quantum weirdness, and the setup is that a cat is in a sealed box. What's often missed is that there is this trigger, so there is this like radioactive particle in there where an atom is both decayed and not decayed. So it's in a state of superposition. We don't know whether it's decayed or not. So at the same time, the cat is both alive and dead. So if the atom is decayed, sorry, not the atom. The atom. If the atom is decayed, the cat's dead. If it's not, it's alive. So the cat is like tied to the state of this atom. So the observation happens when you open the box and you observe the atom. That's when the superposition collapses. So the cat is either alive or dead. So quantum things can exist in multiple states at once. And you'll often see like speculative design, which is a kind of form of critical design used alongside quantum, because quantum superposition lends itself really nicely to this idea of speculative design. So speculative design, this is the futures cone, which was designed by Voros. It was part of, I can't remember the name of the field, but foresight studies. I think this was initially produced in around the 90s, but it's become reproduced by Dunn and Raby, two researchers from the Royal College of Art in London, and they've really popularized it as a tool for design thinking. So the way that it works is at the moment we're on the left where it says present, and then there's an arrow that's kind of going this way, and that's time. And as time expands, there are these different types of futures. So we have the probable future. The probable future is the future that's most likely to emerge if based on the kind of current situations that we're in, if we continue to follow the same trajectory. We have the plausible futures, which are other possible futures, which could happen. And then we have the possible future, which is like kind of unlikely, but it's still a possible future. And the idea of speculative design is for us to find this cone here, which is called the preferable future. So speculative design is often used as a tool to make these like alternative futures possible, tangible, sorry. So you might create a fictional device from one of these futures and bring it back, and then we discuss it, and then we decide whether or not this is a future that we'd like. So I'll come back to that, but one of the artists who sort of talks a lot about, I mean, I would argue that this is a piece of speculative design, is Libby Heaney. So Libby Heaney, if you're interested in quantum art, I'm sure you already know her work, but she's actually trained as a quantum physicist. She did her PhD in quantum physics, and she now works as an artist, and is probably one of the, I think she is the first artist that started making work with quantum computers. So her work treats quantum mechanics as both material and subject. This is a project called ENT, which she made in 2022. And it shows, it's this kind of like big immersive 360-degree environment. It was shown at Arbeit Gallery and lots of other places as well. And it shows an uncertain, unresolved technological future. So we're like somewhere distantly on the futures comb, where she kind of looks at the different possibilities of what could emerge from quantum technology. She argues that at the moment we're at this critical point where quantum isn't really inherently good or bad, but actually what emerges from it, whether becomes a force for good or it has negative impacts on society, will depend on how it's managed, the policy that we put in place, and so on. So it's inspired by Bosch's Garden of Earthly Delights, which is a painting, and it shows this sort of like idea of heaven and hell in it. And then she uses quantum mechanics within this piece. So she really kind of questions the idea of quantum as a technology for society being in a state of superposition at the moment. And the final outcome is still undecided. So she looks at sort of the role of art as a way that invites people to engage with and help to shape these possible futures as well. Moving on, this is the idea of how computation happens. Between the difference with a classical computer versus a quantum computer is that, again, classical computers use deterministic or probabilistic operations, whereas quantum computers do not actively control the outcome, but the probability that it will appear. So this is an example of two types of interference. One is called constructive interference, one is destructive interference. And the way that a quantum computer works is that it will constructively interfere with a state or with a probability to make that more likely. And what happens with constructive interference is like when two waves meet, if they meet at the right point, then those waves are amplified, that chance or that probability becomes larger. Destructive interference are when waves meet at these kind of like opposing sections, and that line becomes less likely. So operations on the system can strengthen some possibilities to make them more likely to appear, or weaken and cancel out others. And there's some analogies that I draw to society and technology in the book chapter that I contributed about how some of these possible technological features are highlighted or made more likely by the systems underlying it. So the infrastructure or media or policies, and other possibilities are hidden or ignored. So our role as observers or for participants is when we act or we decide or we pay attention, we help to bring those certain futures into reality. But the range of possibilities is already kind of shaped by the systems in which we live. There's already kind of defined by the infrastructures that we exist within. So some of the critical questions that quantum artists are considering, and I think is a really interesting area for artistic exploration in terms of quantum art, is which futures are being made most likely, who decides or engineers these probabilities, and how can art or public engagement open up new possibilities that might otherwise be ignored. So the role of art in this instance isn't just showing what could happen, but actually actively shaping which features appear through making them visible. And art can also be used as a tool for constructive interference or destructive interference, just by kind of like amplifying or by shaping which features appear by making them visible. So in terms of CLAPS, this is the final quantum idea that I wanted to think about. So CLAPS and the role of the observer. Hito Sterol talks about how it's not radiation or poison gas that ultimately decides the fate of the cat, but the fact that it is identified, seen, described, and assessed. So art as a tool for imagining technology, it helps society think about and also anticipate these emerging technologies, and it shapes what we call collective visions of what the future could look like. There's from science and technology studies, Jasanoff and Kim argue that technological futures are co-produced through cultural imagination as much as through technical development. So actually the role of the audience and their imagination plays a huge part in shaping that future. And you can see that from examples in science fiction. You'll quite often see headlines where people are saying like times where science fiction has predicted the world, and it will say about how like Isaac Asimov or James Bond predicted this idea of like self-driving cars. We've just got Waymo to London. Or about how Star Trek and Space Odyssey predicted this idea of FaceTime, but actually if you kind of deconstruct it and you think about what else might be happening, actually rather than them being these kind of like prophetic people, that they've actually constructed, like they've contributed to shaping how society imagines these technologies and what technologies emerge. So the idea of social imagination can go a really long way, and art could be used as a tool that shapes those imaginations and then collapses into reality when it is observed. So the last artist I just wanted to show that I talk about in the paper is David Young, and he produced this artwork called Superposition, which I like as a kind of analogy about how audience observation, or the observation of public, and how quantum is communicated to them shapes the direction of it. So this is explored, the principle of collapse of superposition is explored through David Young's Superposition. It foregrounds the audience as a central participant, and the way that it works is he has these clamshell boxes that contain free sealed envelopes. There's a drawing that's generated from a quantum computer. There's an AI interpretation of that drawing. And then there's the original quantum data stored as an NFT. And one of the kind of key points to this artwork is that none of the contents have been observed, not even by the artist. So before opening, obviously conceptually, not literally, this artwork exists in multiple possible states. So there's a kind of direct parallel to Schrödinger's cat there. And his core concept that he's exploring through this piece of quantum artwork is that observation is not neutral, and it actually changes the state of the artwork through the observation. And Young says that the viewer's conscious observation permanently alters the piece, collapsing the quantum state into a single outcome. So the audience role here is not just witnessing, but it's actually actively materializing the work there. So just to sort of summarize some of the points, quantum art echoes the challenges and questions faced by early computer artists. And quantum computing as a medium is fundamentally different with different affordances. So that's an area that we can explore as computer artists, is what kind of new affordances does quantum give? And art as a tool to shape socio-technical imaginaries. And then I was writing something else I've tried off there. Thank you.
Thank you very much. Lots of questions at the end rather than take individual ones. Just to plug the book, what Sarah has told us is down in more detail in this book, in case you want to follow up any of the references. And last speaker, I'd like to turn to Ola Bamboy, who wants to talk about an entirely older style of art, but one seen in quantum terms, I think.
Brilliant. Last. I'm Ola Bamboy. So bit of background. I obviously been around a little while. Yeah, so there you go. I started actually something very, very different. I, moved from Nigeria to Glasgow when I was 11 years old. That's way in the 80s. So, and life was very, very different then. Then I, of course, as most people did, I studied chemical engineering because people in engineering were, yeah. So, Strathclyde University, yes, worked there. Got that degree, and then we had this thing called recession, so there was no jobs. Yeah, so I decided to take up photography, photographic shop. I won't name the name, and since then, worked at Glasgow School of Art and such things, and I kind of developed my own practice of voice, if you like, right? So the work I've got here is called Quantum Governance Studios. I'll explain more of that, right? It sounds really quite big. The interesting thing there is making contested heritage decisions visible. So, okay, move on to that. Yeah, just ignore the tabs on the other side, because I think PowerPoint will need to do it. And then I can between it. Yeah. So, yeah, the background. So I'm actually quite proud of the last one. So that was quite a difficult thing, right? And it taught me quite a lot of things, something very controversial but affecting real people. If you like experimenting on a scale, in a little sense. Before that, I worked with 3D scanners in the 90s. And if you know what those are like, those were very dangerous. You set them and then you have to move away, right? Lots of noise, needles everywhere, and wholly inaccurate and such things. And yeah, so I've done business science and such things. And I also used to do a lot of cultural studies, teaching, and all that type of thing. So quite a few things. Brief things. Maybe one's quite interesting. It is to say, you know, I was involved 2000 in a exhibition called Bridge the Gap in Japan, which was art science. So you had, we're lucky to sit at the table with Zellinger and such things. And I asked them about making objects appear in two places at the same time. They have a few ideas that informed the exhibition that happened in the Ukraine and so on. Yeah. I've always had the idea of like bending the rules. So what's this about, right? The work I'm showing has two objects. I'll make this quite quick because it's quite visual. Two objects with contested sort of qualities, right? So we have her there, you know, I'll be very precise, object 27.1199.8, which is there. What's interesting about that object is only until probably 4 years ago, you wouldn't really see the back of it to see where it's actually been damaged. But being cunning, I got a scan of this in 2000, you know, which is at that time was a grand scan of I think something like 200,000 vertexes. So that was like, you know, hardly anything could process that, right? You know, it's probably, you know, so that I would actually say that scan itself is actually legacy and, you know, kind of like endeared in a sense. And the idea here is to, how should you say, right? You know, to hand over the original concept of the show was to make this object in a place that people could customize it and then repossess it and download it and print it. So it happened 20 odd years ago, but it's made possible now. That's what that object is. The other one is not. Yeah. We all know what that is, right? Yeah. And so you now see the contested sort of avenues in terms of what I'm trying to sort of proposition. I think it's interesting to put these two objects together in the first place. You know, there are ethical questions about that, about whether it was right or wrong in a sense. But if we imagine that there are lots of similarities that they both have, right, in a little bit of a way, and the work that hopefully you get to see outside hits these two things that we should maybe know about, you might have certain feelings about it, and asks us to vote what happens to them. So it's a training thing, right? It's very, very simple. I mean, we've had Q gates described and so on, but this is a very simple 2 qubits, right? So it's very small. It's supposed to work, right? And you would decide whether you think A should be returned, B should be done. You put a comment in, all completely hashed. It doesn't take your name or anything like that, and it votes. It calculates, right? Because the rotation of the gates and such things, which is all sort of fun stuff. What it's trying to do, it's a long experiment, just beginning about a year ago, right? So I'm not sure how long it would take, but in an ideal world, it should help us to shape the circuits in the real time, right? Which is actually the decision arc in a sense. Now why am I interested in this? I guess from my civil service sort of background in a sense, you always have diametrically opposed situations, right? Being me, I've always tried to find some commonalities between the two. I always believe there should be something all of us in here should be able to agree on. Might take a while. So it's the power of the quantum machines, right, is to make that happen, right? So what you see outside there is there's some diagrams printed on the wall, but they're snapshots. I mean, heaven knows what's happening with the equation, right? Whatever it is. You could say that it holds multiple futures in superposition, in a sense. Yeah. There's no right, wrong. Yeah. And it wouldn't be complete without something AI, would it? You know, but here, this is just a very simple model that's running and learning from what actually happens to the votes and actually what happens. And let's say it's been tricky to try and, how should you say it, so to sort of lock its horns, right? To make it do something very simple. So ask it and the program is just to basically simplify things. So over there, you might say that, oh, the trend is towards here. It talks in general language, right? As far as possible. So, yeah, we know about that. I'm not going to go over that anyway, except the last one, because I think that's quite important. And for me, that's the whole point of it, right? That every single decision and choice leaves an auditable trail, which then impacts the overall decision. Sounds weird, but yeah, for me, it's not a metaphor. It's actually a potential way of, what should you say, decision resolution engine, which is what we could actually do with, right? You know, I think. I'm not gonna bore you all that much because we're probably all needing our drinks or whatever that is, right? But if you were to step over there, I can actually go through it and see how it works. But more importantly, like that, it works online, and you get take a picture of that. You can, you know, play around with it at your leisure in a sense, and it needs people to work on it to actually learn. In a sense, right? So as we all mentioned, there is no right, wrong. I guess if we didn't vote, do anything to it, we can't really complain what happened. But in a beautiful world, what I would like to have is just, let's say this is like a pattern, right, on the wall, right? Every single person here should be able to say, I contributed that part. I'm not sure what the whole thing might look like, right? It can look like anything. So, that's all. There's also a rather theoretical saying in there.
Sure, thank you very much
for that. But a pleasure. And yeah, speak to you later. Hopefully.
If any questions to any members of the panel?
I have a question. You know, we have seen, I mean, I've been involved in the media before, I've been involved in the fashion industry before and all that. We've seen all the airbrushing, we've seen all the computer graphics, we've seen it all. But with AI, you know, I saw this in this Indian thing where they have basically they're making these videos where they are basically they're making the actors look younger, you know, and when they do flashback scenes, they make the actors look younger. And now it's coming into the wedding videos where they're slimming people down, they're airbrushing people and everything. Is there a way where I could look like I did when I was in my youth? Quantum, whatever you use. Make me look more athletic, you know, fresh face, bigger eyes, the cheekbones, the jawline, everything that I had that I lost. I want it all back. So can you recreate that?
Unfortunately, I think your state is already measured in its current state. So I think it's against the quantum computing law, which is the quantum mechanics. But briefly speaking, I think you can maybe build some kind of visual algorithms so you could actually do something. For example, you access through the images, which is the 2D data. And we could easily manipulate with computational procedures while exploiting something in those pixel data. And if you can find a way,
find a way. You do.
I mean, this talks proposed is inviting artists and creative ideas for the quantum computing domain. So now your turn to make it happen. You will make it happen. I will promote it. I think we will bring out an app that can make people look fabulous again.
One thing we can be sure of is if you manage to do this, there's a fortune in it for you somewhere.
Yes.
Gentleman right at the back there, will you ask a question?
Yeah, I was. I suppose it's one aimed at the people who are looking at research, the whole field of quantum art, applications and contexts. I wonder in coming across artists and their practice, whether they'd ventured into related fields of physics. Like one thing that springs to mind is statistical or quantum mechanics, which, real nutshell here, for those who don't know, is like taking a load of quantum particles, averaging them and being somewhere near the quantum world and the reality where you get your like Ohm's law and all the rest of it. I just wondered if that probabilistic multi-particulate approach had been looked at in an artistic context.
Did you want to comment on that?
Yes. So when you look at the voting, for example, when people vote, you've got all the rotational things in a sense, but in the collapse element and the coding in a sense, it does take a probabilistic but that probability itself is moving, right? At all times, right? So to answer your question, yes, we can do that, right? But there will be a price to pay at the other end, right?
Mm-hmm.
Yeah. So just
I'm happy to pay the price. Yeah.
In a kind of sense, you would disrupt something else, right? Because you're forever entangled, right? If you like to, in a kind of simplistic way, in a little bit of a way.
I know it sounds very vain, but
there is nothing like that, years people have been wanting to have multiple things in different perspectives. But I think you're right, the gentleman at the back there is, how should I say, there has to be some certain, for me, the attraction is there's a kind of certain level of rigor in there that obeys the real rules, in a sense. So yes, artists can, for me, interpret that in a sense, but within certain boundaries as well that are correct. And I think to me that's the challenge and the fascination that
there are boundaries for art, though.
Yeah.
Geoff, are there any questions from the Zoom audience?
No, I don't think so.
Okay.
Hi, I thought that was fantastic. All three speakers and of course the people introducing, amazing. So my question is regarding noise and quantum decoherence. A lot of researchers are, putting the efforts in order to reduce noise and to hold a reality from superposition. So my question is to each of the speakers, do you see noise as an opportunity or a threat to your work?
I think it's based on what you will do with the computational procedures. So if you want to, for example, if you want to kind of classify the data, or if you want to simulate the interaction between molecules, so it's another research field, it's a quantum chemistry. If you want to simulate that nature, probably noise won't lead the good result, but there's always a workaround. For example, imagine you are doing the classification task, and imagine you need to deal with the complex data, and you need to kind of map those complex data onto the kind of interpretable dimension so that you can actually see how those data points are distributed across high dimensional Hilbert space in quantum computing. And if you see those noise as some kind of affecting those features, so you are putting some distinguishable features between those data points, and based on noises, those data points will drift each other or do whatever they want to do based on the hardware noise. And you can actually pick some QPUs, because those QPUs have different noise models, and it will introduce different aspects to data. And if your task is successfully done in this QPU, then you can continue your research on that one. And for the noise itself, it will somehow kind of amplifies the probability about what you actually want to do, so based on your viewpoint. In this case, yes, it will be useful, but it's based on what you will do with those noises, what you will do with the differences between the probability that you wanted to observe and the probability that actually turns out after the measurement. So that might be my answer, if that's helpful.
Interesting.
Thank you.
Yeah, I think just quickly on that, I think it's a detailed explanation by Astrid. I think for me, it's a little bit like the noise is the individual biases of of the individuals, right? So within my context, so it's very, very important, right? Because controlling the noise is tempered with certain things, right? You know, can you, shouldn't you, or whatever, right? In a sense, and actually, difference between, apologies if there are science and engineers in here, right? There's the scientific thing, there's precision that works in the lab, and then there's the making it in the real world, right? Where the engineers add all the correction factors to make it work. You need both. You know, the theory is quite good, but the delivery of it in real life requires noise. Yeah, if that makes sense. But anyway, that's
Fascinating.
Right. I was very interested in Sarah's comparison of the early days of digital art and the way quantum's come in now, because in the 1990s, I was very much at the sort of forefront of the early days of digital photography and working with a number of suppliers and beta testing stuff and all the rest of it. And I understood from quite early on that digital photography was going to change the entire industry of photography, the way we recorded pictures and everything else, and that it was unstoppable when an awful lot of the industry seemed to hope it would go away. And I wondered if any of the speakers would like to just comment on whether this is unstoppable and you need to be really boned up on it as quickly as you can in consequence.
I think one of the things I found from being with the political science group is that quantum used to be very theoretical in terms of its research. And obviously since there's been like physical applications of quantum, there's been a huge like bubble that's boomed around it. And there's a lot of there's so much misinformation in quantum about like what quantum can do, what the potentials of it are. And a lot of the physicists that I've spoken to are still very sort of unsure of like whether or not it's a tangible future. Just the talk from James at the start when he was saying about how far away we are from being able to use quantum to decrypt like online encryption, and about how like the noise is still such an issue that it's actually like the reason that quantum is such a geopolitically like tense thing at the moment. Like in research, we're banned from working with people from countries that aren't deemed like friendly because I don't know, like espionage and stuff. But yeah, like actually it's interesting to hear how far away some realities actually are. So I think it's a case of cutting through a lot of the hype at the moment, whether or not it's a future or not. I mean, Astrid, you're working with the actual applications of it, so you have a better idea of the time.
Isn't she fabulous?
No way. So I think my point is reality, of course, now we are still like a lot of QPUs are governed by noise. And of course, a lot of industry professionals, researchers, scientists, engineers are working very, very hard to bring the fault-tolerant quantum computers possible. So, I mean, bringing, for example, IBM's roadmap, IBM kind of talks about 2030, but obviously it's an industry roadmap, so we will never know until those hardware companies will do something.
I was going to say, on the policy space, is there not some direct lessons learned and applicability from what's being talked about in AI at the moment? Albeit I think AI is probably 5 to 10 years in front. I think that not the details, but the context, the way people think about the policy of using something that's a bit, quote unquote, enigmatic and different. I'd imagine there's a lot of things, lessons learned even now that are coming as people find it could do some things. It's not the silver bullet that's going to rescue the UK economy or what have you that we're currently being told about. Right, I just think there's probably some analogy to be drawn.
Yeah, I mean, democratic decision making. Just for start, I mean, heck, I mean that's quite. There are. I think it's a very, very good point the gentleman makes. You know, but I think. But then that's really no different from art and society and all things that we really know about, right? And I think that's what's great about this particular show, to certainly be part of it, that it's something that it's not about the accuracy or the appropriate, in a sense. It's really something happens, and then through the mistakes and such things, what do we learn from that, right? Does that improve, you know, from the physicist side, a bit more thinking in real world how things work and vice versa? So I think, yeah.
Yeah, I think they're like very rapid with the policy with quantum compared to maybe they were with AI. Like, it's even like the possibilities that something could become a reality is like policy very fast, I think.
Yeah.
Just time for one last question.
It's kind of a follow on from that, so you teed me up nicely. From an artistic perspective, in terms of like licensing and copyright and I guess intellectual property, what do you think the government could put in place in terms of ethics to protect intellectual property if we're to look back from the mistakes that have been allowed happen with AI and machine learning?
Well, yes, that's why shows like this are very important. Yeah, I think artists have to. I mean, I'm interested in a different way in terms of different AIs for artists as a kind of tool. So I think you need to do it right, because otherwise, there are things being encoded within the learning of AI that we don't want to get too deep into that themselves are infantile compared to what artists can offer. So yeah.
AI is back in those days when they first introduced as a neural network around 1890s. I mean, it might be really, really hyper. Imagine machine learning something from you and talking to you. But obviously AI nowadays, originally, I think when I was in high school or middle school, I think I heard more about machine learning, the term, and now everyone's using artificial intelligence, AI. And while all of those hypes are coming and going, I think that's the moment when we learn that all of those emerging technologies are very like connected to each other and also to us, because we are the users of those technology. And I'm honestly glad that this conversation is going on right now, because I can see that actually we could talk about how this technology will shape the policies in the future. How will we learn something while we are making the applications using emerging technologies, so that those technology won't fall into some weird people's hands, and actually it will make something useful or something good, like adding good values for humanity. And I think for quantum, I think that's why it's important about this talk, and that's why it's important about this conversation, and that's why me and other speakers and David set up this exhibition and etc. to deliver that information, so that everyone must be introduced and welcomed in the conversation of quantum technology, so that people can actually see what it can do, and what is the hype, and what is the ongoing research, and what is the problem that we want to actually solve through technology. And yeah, that's just the thing that I wanted to address. And so I'm glad.
James, did you want to ask a question?
I want to make a comment on the question about can we learn from AI? The answer is we will learn from AI, since AI was the first standardization subject to really have societal questions. When we standardized, we had British standard for seatbelts. No one asked whether that standard affected fundamental rights. And so on. And yet we are doing that with AI. So in some sense, quantum will learn, because AI has had that painful, I said we was feeling, learning experience. Thanks.
Could I just finish by saying, it's past, 4 things really. First of all, thank you very much to the speakers. I've learned a lot, certainly. Secondly, thank you very much to you for coming along here, and also to those people who are, I think, watching us on Zoom. I can't see you, but you can hopefully see me. Thirdly, we have got a book here, if anybody is interested, which takes some of these arguments further. I brought a few along to sell. I rather think I underestimated, but I have got a few left. If anybody's got £8 handy, you can buy one now. Otherwise, we've got QR codes all the way around the building, which will take you straight through to Amazon, who will send you one immediately. And lastly, just to remind you, if you want to download and set up the Moth Quantum brush, there's details. These are free. Here are details. Come and get them from me. Now, next door we have glasses of wine, and we have Astrid and Ola demonstrating their toys, if I can call it that. It's very, very interesting. Thank you very much.